This lecture is going to finish off chapter 3 of the textbook, and I'm going to go over in this lecture some calculations involving the mole concept that we learned about in the last lecture. We'll start out by going over how we calculate the percent composition of a compound, and then we will see that we can use the percent composition to calculate the formula of a compound. And that's a really useful calculation because it is a way to determine the formula of an unknown sample from the percent composition, which can often actually be measured by an experiment. And I'm not going to go into detail about the experiment, but I'll just show you this picture from the textbook. You can see at the bottom shows that, for example, if you take a sample and burn it, and then measure how much water and CO2 is produced, that can tell you how much carbon and hydrogen is in the sample. So we'll go over how we calculate formulas of compounds. Now, first of all, section 9 of chapter 3, percent composition. So we saw last time that the formula of a compound tells us how many moles of each element are present in 1 mole of the compound. But we might also want to know how many grams of each element there are in a certain amount of compound. And so we can express that through the percent composition, which is the percentage of each element in the compound by mass. So it's the percent of the total mass of a compound that is due to each element. So for any individual element in a compound, you can calculate its percent by mass through this formula. So for any element X, you take the mass of that element in 1 mole of the compound and divide by the mass of 1 mole of the whole compound. Now, the mass of 1 mole of the compound, of course, that's just another way of saying the molar mass of the compound. So you're dividing by the molar mass. Now, on the top of that expression, so we learned in the last lecture that when you have 1 mole of the compound, the moles of a given element you have, it's just how many times that element appears in the formula. So the mass of that element in 1 mole of compound, you would just take how many times that element appears in the formula times the molar mass of that element. So we can rewrite that formula as the percent by mass of an element. You take the number of atoms of that element in the formula, and that is generally just going to be the subscript after that element in the formula, assuming that the element only appears in one place in the formula. Otherwise, you have to add up all the places that the element appears in the formula. So you take the number of atoms of that element in the formula times the molar mass of the element, and then divide by the molar mass of the compound, and then multiply by 100 to make that a percentage. So let's do the example of a compound with the formula C2H6O. So what is the percent composition of this compound? So that's going to be the percent by mass of carbon, the percent by mass of hydrogen, and the percent by mass of oxygen. And again, we can use the formula that I just showed you. Now, in each case, we're going to be dividing by the molar mass of the compound, which is 46.07 grams per mole. So this was the example in the last lecture. We saw that C2H6O has this molar mass. Okay, so we can go through and do the calculation for each element. Now, first of all, for carbon, the molar mass of carbon is 12.01 grams per mole, but we multiply by 2 because there are 2 carbons in the formula. And then we divide by the molar mass of the whole compound, which is 46.07, and multiplying by 100 to get a percentage, we get 52.14%. And since I use the molar masses to 4 significant figures, I'm just writing the percentage to 4 sig figs also. Then we can do the same thing for hydrogen. So there are 6 hydrogens in the formula. Hydrogen has a subscript of 6. Multiply by the molar mass of hydrogen, and again divide by the molar mass of the compound, multiply by 100, and I get 13.13%. And then for oxygen, there's only 1 oxygen in the formula, so I don't have to multiply its molar mass by anything, so I just take 16 grams per mole, so it's times 1 in other words, divided by the molar mass of the compound, multiplied by 100, and I get 34.73%. Okay, so what did we calculate here? We calculated that in this compound C2H6O, 52%, so just over half of the mass of the compound, is due to the carbon atoms. Only 13% of the mass is due to the hydrogen, which makes sense because hydrogen atoms are very light. And then the remaining percentage is due to the oxygen atoms. So again, in each case, I was dividing by the molar mass of the compound. It's just what went on top was different. It was just the molar mass of each element times the number of that element in the formula. Now, one thing to be aware of, if you are calculating the percent by mass of all the elements in the compound, the whole percent composition, notice in total there must be 100%. And in fact, if you add up my numbers there, I get 100.00%. So if you're calculating the percent composition of a compound, to double check, just make sure that your percentages add up to 100. Next, I want to do the reverse calculation. Now, I said at the beginning of this lecture that you can take the percent composition of a compound and calculate the compound's formula. Before we get into that, though, let's talk a little bit more about some different types of formulas. So we have learned about the molecular formula for a compound. So, for example, water is H2O, and that tells us that every water molecule contains exactly 2 hydrogen atoms and 1 oxygen atom. But there's something else that H2O tells us. It tells us the ratio of hydrogen to oxygen. So in any sample of water, it doesn't matter how many molecules you have in total, there are going to be twice as many hydrogen atoms as oxygen atoms. And so a formula that gives us the simplest whole number ratio of each element in the compound is known as the empirical formula. Now, in some cases, such as in H2O, the empirical formula is just the same as the molecular formula. But in some cases, though, you can simplify the molecular formula to get a simpler ratio. So the reverse of that, what that means is that the molecular formula will always be a multiple of the empirical formula. Now, it may be the empirical formula times 1, as is the case for water, but you may have to multiply the empirical formula by a certain whole number factor to get the molecular formula. Now, for ionic compounds, as we've seen before, the ionic compound is the formula of an ionic compound is the formula of the formula unit, which is the simplest ratio of each ion. So that is an empirical formula. But for molecular compounds, the molecular formula tells you exactly how many atoms of each element there are, which may not be the same as the empirical formula. So for example, here are 2 compounds, C2H2 and C6H6. Notice in both cases, the number of carbon atoms and the number of hydrogen atoms is the same. So there's a 1-to-1 ratio of carbon to hydrogen. So we would say that the empirical formula of both of these compounds is just CH. Now this picture from the textbook shows you a picture of 3 acetylene molecules, so 3 C2H2s. Now notice in total, that has the same number of atoms as 1 C6H6. That also means that 3 acetylene molecules would have the same percent composition as 1 C6H6 molecule because they have the same number of atoms, but the percent composition does not depend on how many molecules you have. So that leads to the conclusion then that molecules with the same empirical formula will have the same percent composition. So that means that the percent composition will allow us to calculate the empirical formula of a compound. So the percent composition would not distinguish between C2H2 and C6H6 because they have the same empirical formula. So let's go through then, how do we calculate the empirical formula of a compound from its percent composition? This is in section 10 of the textbook. So I'm just going to jump straight in with an example. So the compound lactic acid contains carbon, hydrogen, and oxygen, and you can see the percentages of each element by mass. Okay, so here are the steps to go from the percent by mass of each element to the empirical formula. First of all, let's start out by assuming that we have 100 grams of the compound. Now, why do we do that? It just makes the math easier. So as we said before, the percent composition does not depend on how much of the compound you have, so you can assume any amount you want. But if you assume you have 100 grams in total, a percentage of 100 grams is just the same number of grams, so the percentages become grams. Then what you have to do is you have to take the grams of each element and convert that to moles. And then you look for the simplest whole number ratio of the moles of each element, and that ratio is the empirical formula. So let's go through these steps for lactic acid. Again, here are the percentages of the 3 elements, or actually I have just converted them to grams. Again, if we assume 100 grams in total of the compound, the percentages just become grams. Now remember, you don't want to try and compare the grams of each element. That's not going to help you. The formula relates the moles of each element. So we have to convert the grams of each element to moles, as we learned previously. So you want to divide the moles of each element by its molar mass. So the molar mass of carbon is 12.01 grams per mole. And so that gives us 3.33 moles of carbon. Now we can do the same thing for hydrogen. We take the mass of the hydrogen, divide by its molar mass, which is 1.008 grams per mole, and we get 6.66 moles of hydrogen. Then for oxygen, we take 53.3 grams of oxygen, divide by the molar mass of oxygen, which is 16, and we get 3.33 moles of oxygen. Okay, so then the third step is take the moles of each element. So we've calculated the moles of each element in 100 grams of compound, and see if we can come up with a ratio of those moles. Now in this case, it's pretty easy. We can do it by inspection. In other words, we can just look at the numbers and see the ratio. Now, first of all, you can see that carbon and oxygen have exactly the same number of moles. So that means they will have the same subscript in the formula. And you can see the moles of hydrogen, that's just double the moles of carbon and oxygen. So we can see the ratio there is 1 carbon to 2 hydrogens to 1 oxygen, which gives us a formula of CH2O. So that's the empirical formula of lactic acid. Now going on to the next section, what if you wanted to know the molecular formula of lactic acid? Now we said that the percent composition only gives you the empirical formula. We also said that the molecular formula for a compound is going to be some multiple of the empirical formula. So it could be the same as the empirical formula. It could just be CH2O. It could be double, which would be C2H4O2. It could be 3 times. It could be 4 times, and so on. So how do we know which of these is going to be the molecular formula for the compound? Well, we need one more piece of information. And that piece of information is the molar mass. So if you know the empirical formula of a compound and the molar mass of the compound, you can calculate its molecular formula. So going back to our example of lactic acid, we found that its empirical formula was CH2O. Now let's say somehow we also were able to find out that the molar mass of the compound was 90.08. So what is then the molecular formula of lactic acid? So what we have to do, so we just saw that the molecular formula must be some multiple of the empirical formula. What would we have to multiply the empirical formula by to end up with something with a molar mass of 90.08? So a good way to approach this problem is say, okay, look at the empirical formula, CH2O. What would be the molar mass of that unit? So what is the mass of 1 mole of CH2O? And if you calculate that, it turns out it's 30.03. So what do we need to multiply 30.03 by to get 90.08? Okay, I think that should be pretty clear, but if it's not, if you take 90.08 grams per mole and divide by 30.03, you can see that is going to be almost exactly 3. So that tells us that in order to get the correct molar mass, you have to multiply the empirical formula by 3. So we take CH2O, multiply it by 3. In other words, multiply all the subscripts by 3, and we get C3H6O3. So that is the molecular formula of lactic acid. And in a problem like this, of course, always check, since you're given the molar mass, make sure the formula you come up with does have the correct molar mass. And C3H6O3 would have that molar mass. Okay, so let's summarize what we've done so far. We started with the percent composition of a compound. We just turned those percentages into grams by assuming that we had 100 grams in total of the compound. We divided the grams of each element by the molar mass of the element to give you the moles of the element, and then we converted those moles to the simplest whole number ratio. That's the empirical formula of the compound. And then if we also have the molar mass of the compound, you can solve for the molecular formula of the compound. And that's summarized by this little chart here. But what I want to do now to finish off is back up to step number 3. Now in lactic acid, we saw that once we got the moles of each element, that was step 2. Step 3 we did by inspection. We could just look at the numbers and we came up with the ratio pretty easily. But that's not always going to be so easy. So sometimes this step can be a little bit tricky. So what happens if you get the moles of each element in the compound and you cannot come up with a ratio by inspection? There's some mathematical tricks that we can do. So a good procedure is look at the moles of each element and see which number of moles is the smallest. And then divide all of the moles by that smallest number of moles. Now keep in mind, once you have the moles of each element, you can multiply or divide those numbers by anything you want, as long as whatever you do to one element, you do to all the elements, because we're just interested in the ratio of the moles of each element. So if you multiply all the moles by a certain factor, you're not changing that ratio. So you can divide the moles of each element by the smallest number of moles. Now, in some cases, that may give you whole numbers. If that's the case, then you're good. But if not, then probably it's going to end in a fairly simple decimal, something like 0.5 or 0.25 or something like that. And then there should be a small factor you can multiply each number of moles by to get whole numbers. And that's summarized in this table. So if you end up with some moles that end, say, in 0.5, of course, if you multiply that by 2, it's going to give you a whole number. So just multiply all the moles by 2. If it ends in, say, 0.33, that's a third, so you multiply all the moles by 3. So let's look at an example of following that procedure. Now, maybe this lecture is giving you a headache with all this information, so if that's the case, you might want to take an aspirin. So let's talk about aspirin. The aspirin molecule, it also is made up of carbon, hydrogen, oxygen. And by the way, all my examples have involved carbon, hydrogen, oxygen, but it doesn't mean that these calculations only work for those elements. It works for compounds with any elements. So here's the percent composition for aspirin. So like before, we want to convert the grams of each element to moles. So I divide the grams of carbon by the molar mass of carbon, which gives me 4.996 moles of carbon. Do the same thing for hydrogen. I get 4.440 moles of hydrogen. And then I take 35.52 grams of oxygen, divide by its molar mass. And I get 2.220 moles of oxygen. Okay, so we can see by inspection that the moles of hydrogen are double the moles of oxygen. It's not really clear, though, what ratio then the moles of carbon would be. So we said, remember, that in situations like this, you can divide by the smallest number of moles. Now, the smallest number of moles, you can see, is the moles of oxygen, 2.22. So I'm going to divide the moles of oxygen by itself, 2.220, and of course that gives me 1. If I divide the moles of hydrogen by that same number, it gives me 2. If I divide the moles of carbon by that number, then I get 2.25. Now the carbon is still not a whole number, but notice 2.25, that's 2 1/4. If I multiply by 4, then that's going to give me a whole number, just like we saw on this table. If you get a subscript of 0.25, just multiply by 4. So I multiply the carbons by 4. Now that just means I have to multiply all the other elements by 4. And 2.25 by 4, that gives me 9 carbons. 2 times 4 gives me 8 hydrogens. And then I have 4 oxygens. So that gives me then a formula of C9H8O4. So that is the empirical formula of aspirin. And actually, if you look up the molar mass of aspirin, this formula has that same molar mass. So this is, in fact, also the molecular formula of aspirin.